So we were talking about Poisson regression. And in the Poisson regression, right, we're modeling, one way to think about it is that we're modeling the count at each cell of the contingency table as a Poisson variable. Now, remember we had this idea early on when we were talking about sampling distributions that if I have a contingency table, let's make it, I don't know, 2 by 2 contingency table, and in here are counts, I can think about mu1, 1, mu1, 2, mu2, 1, mu2, 2, mu3, 1, mu2. Well, mu being so things I could put in here include n, which would be the observed count, p, which would be the probability, thinking of it as a multinomial distribution, and these mu's, which would be the expected count from thinking of it as a Poisson. Right? So we had this idea that given a sort of a mu plus plus or an n plus plus, depending on what I'm putting in there, we could factor a Poisson sample table into a Poisson variable for the grand total, and then a multinomial distribution here. And if you sort of turn that around, what it suggests is that it's possible to use this idea of Poisson regression, like we did last time, for multinomial data. And so today I want to talk about what that might mean, and what idea that leads to. So in other words, what we're going to do is say we have a multinomial table. We have a multinomial sampling. Maybe we have a study. We have some fixed number of individuals. And just as we could, in one direction, pretend it wasn't Poisson, pretend it was multinomial, we can pretend that instead of being multinomial, that it's Poisson. Or yi or ni are Poisson, and they have means mu I, which is equal to this grand total, and I here is indexing the cells, so there's 6 of those possibilities here, times the probability for that cell. Okay, so we have a multinomial distribution, that will be just the p's. If we add in the grand total over here, then we can think about it as a Poisson mean with parameter mu I. So then we can continue, and we're going to want to use the log link, and we can sort of fit this thing as a Poisson regression. With the caveat that we need an intercept. If we didn't have the intercept, then we don't have a free parameter that can handle this. So this intercept, in the case of a multinomial distribution, isn't really a free parameter that we're estimating, because we may have fixed that number in our design. Instead, you should think about it as a normalizing constant. Right, so for example, if I think it's multiplicative, if I have a probability model where I say have an independence model, alpha 1, alpha 2, beta 1, beta 2, and I just say, okay, let's build an independence model, I have alphas and betas, and I assume that here this is alpha 1, beta 1, alpha 2, beta 2, alpha 1, beta 2, and alpha 2, beta 2. And I just say that alpha and beta are non-negative. So these could be like potential functions. And that's our only assumption, and this is kind of one of the implicit assumptions in some of the models that we've talked about. Then in order for this to represent a table of probabilities, we would need a further constant, right? And that constant would be 1 over the sum of these numbers. 1 over alpha 1 beta 1 plus alpha 2 beta 1 plus alpha 1 beta 2 plus alpha 2 beta 2. Right? If I multiplied each of these quantities by that, then I would get probability distribution. And so this last piece, the intercept here, should be thought of as this kind of constant or partition function that allows it to meet the constraint either that the probabilities sum to 1 or that the sum of all the counts is equal to the global grand total.
Excuse me. I was wondering, so what would be a real application related to the Poisson regression? How about we have a the Poisson arrival rate, and in that way, we just model it as a Poisson, the regression. Like we have a multi-arrival rate, say, and also the inter-arrival rate is exponential. So in that way, in that kind of
yeah, so like for example, the skier data, or through this kind of thing. Anytime you have what I'm saying is, anytime you have a multinomial, you can think of it as a Poisson, as long as your model has an intercept. So we've had lots of examples of things that could be modeled by multinomial distributions, and if you're willing to make that leap, then you can also think about them as Poisson. Okay, so the idea is that this type of correction is what we end up calling a log linear model. One way to think about this is to say that we have some vector of probabilities, and we're saying that that's equal to some vector of parameters, times some kind of parameters times some design matrix that describes the model. And we have and so so let's say this will be number of parameters, let's call that P, and this will be sort of number of cells, so this is P by N, where N is kind of the number of cells in the table, or the number of possible outcomes. And so in other words, one of the ways to think about what the log linear model is assuming is that this vector log P lies in the linear space spanned by the rows here of X. And we'll see in a moment some examples of this kind of matrix and what it does for us in terms of understanding the model. But the one idea is to say, well, suppose you have some variables. You have variable A taking values 1 up to I, you have variable B taking values 1 up to J, and C taking values 1 up to K. When we think about what we observe in the experiment, or alternately, what interactions, what associations we look at in the model, what we're essentially doing is counting how many times things happen, right? So if I only interested in the marginals, I'm counting how many times did I see a 1 for A, how many times did I see a 2, marginalizing the others, ignoring the others. For B, how many times did I see each of the outcomes for C? If that's the only thing I consider, what I get out is an independence model. And if I want to consider some associations, like a term for AB, I count how many times I saw 1 for A and 2 for B. How many times I saw 1 for A and J for B, and so on. Right? And so each of those kind of associations that I could look at can be represented in this as sort of a constraint. Right? The model that I get out should agree with those counts as much as possible. So in the independence case, it's possible for them to agree exactly, right? The model is defined by saying, well, it's just you take the model which gives me the right marginals, multiply them together, and that gives me the joint distribution. And in the other, in more extreme, more complicated cases, you can also do that. You can say, just, I want to pick a model which, if I look at the empirical distribution of the data, and I multiply by some matrix that represents which coincidences I'm counting, I get out something which agrees with what I've seen. So when we're doing these kind of log linear models, there's an analogy to ANOVA models, if you remember those from another sort of class. The difference is that our response variable is not really an honest variable. So in an ANOVA, you do something like, have 3 variables, A, B, and C, and the effect on some 4th variable on a response. And here, our response is not really a variable, but it's the log probability. We're kind of doing a regression on the log of the probability. And so some of the ideas from this about interaction stuff make sense, and some of them don't make as much sense, because really we're just talking about, we're talking about the log probability of something happening jointly. We're talking about just an association. It's not really an effect. And similarly, so if we were doing kind of an ANOVA, we might say that it's okay to we might remove a main effect. Right, so we could say, well, A, B, and C are all affecting some response variable, D, and maybe I want to do the model that doesn't have a main effect for A, and that would make perfect sense. But for a log linear model, we don't want to do that, because removing the parameter that corresponds to the effect for A is like assuming that there's a uniform distribution over all of these outcomes for A. So the effect or the parameters for A, assuming a uniform marginal for A. Silly. And we don't want to do that. And that's kind of the reason why the simplest model we would consider for a 3-way table would be the independence model. Okay, so let's, now I'm going to write some equations and actually write down some of these models to be a little bit more precise. Okay. So what's our goal? So we have a table, let's say, first of all, just two-way. We have a two-way table, I by j. And we have some expected counts. We're building a model of expected counts. And there are 2 random variables, A and B, which are categorical. And we would like to model this. And so this is n plus plus, the grand total, times some probability for that. Right? That's our model. So if we said that the link that we're using, when we're thinking about this as like a Poisson regression or GLM, is the log link. So we take the log of this, and what happens when we take the log of this? Okay, so that looks a bit better. So this is sort of the thing which is going to correspond to the intercept. Now be careful, because it's not true necessarily that the intercept is equal to this in general, but it's going to have to change according to what we put in here. And then we have another term which looks more like the log link that we used before. And so say we take a saturated model. That will look like that the log of the cell value is equal to some constant or some global count parameter, which sort of corresponds to this, plus something for the rows, something for the columns, and something for the interaction, which depends on both rows and columns. And if I have more than 2 rows and more than 2 columns, I'm going to need more than one of each of these parameters. And the notation that we use for the ANOVA and for the rest of the course is that this global parameter is given the name. Oh, let me start writing it up. I'm not sure everyone can see that. I'll write it up here. So this global parameter is called lambda. And then, so are all the other parameters called lambda, but we have to label them by which variables they correspond to. So these ABs and ABs and the exponents are not exponents. It's just a label that says, I have a bunch of parameters. I'm going to call them all lambda something. They're indexed by what value it takes and what variable it corresponds to. And there's one other wrinkle, which is that we need constraints. And so this is a little bit of a subtle issue. We've dealt with it in one form already when we talked about baselines and different strategies for modeling sets of odds ratios in a multinomial response. So, or different ways of encoding dummy variables. So the problem is that if I just look at this equation naively, I have way too many parameters, right? So if j and I and j were equal to 2, this would give me 5 parameters just up to here, right? And we know I don't need 5 parameters to model an independence model, right? So we have too many. I only need 3, including this one. So we need some constraints or some way of cutting down this total number of parameters to reflect the fact that there's redundancy among them. So there's some choices of that, but one way to think about it is that we should make all of these things sums equal to 0. Lambda j, ij, lambda ij equals 0. And there are other ways of making this choice. Okay, so now we're assuming that the counts in each cell are Poisson with, so Nij is Poisson. Each Nij is independent Poisson Uij. So what would the independence model look like up here? I said that's a saturated model. What would the independence model be? No, it's an independence model. I assume some of these things are 0. Yeah, about this one. That would be independence. which is just a, you should, if you exponentiate everything, what we're saying is that mu ij is equal to some adjustment. I don't know, let's call it z inverse. I can call it whatever I want. Maybe not z inverse, let's call it just mu, times some things for the row and something for the column. So I said that this parameter, the lambda parameter, is there to make sure that the whole model satisfies the global constraint in the sense that when I add up all the rows and columns of the table, I get an m++, that should equal the sample size. When I add up the probabilities, I get a p++, and that should equal 1. And lambda is there to make sure that happens. And that will be also true if I made a larger table, right? That was 2 by 2 by 2, or 2 by 2 by 2 by 2. If you think about it, well, okay, so then if I did that, what happens to the subtables in the higher order table? Right? The subtables can't correspond to this global parameter, they correspond to some other parameter, except that these subtables also have totals, right? In fact, anything I can count, like how many times was A equals equal to 2 and B was equal to 3 in the sample set. If I count that, that will also be a total. And my model is not going to be a very good model unless it can agree with that total. So in fact, you can think about these parameters, all of these parameters, as representing constraints that your model has to satisfy. In fact, there's a way to set up the solution for this that uses Lagrange multipliers, and as before, and these lambdas are actually the Lagrange multipliers that show up in that calculation. I'll do that later on. So really, it's like a series of nested constraints that we want to look at. So this thing is an overall effect. These are the main effects for each variable, kind of the grand mean, the deviation from the grand mean, or the effect of being in row I, the effect of being in column I, and then this thing is the effect of the joint. Okay, so but we have this problem that there are too many parameters, which is in the 2 by 2 table already visible, and we want to think about how this design matrix idea or this log linear constraint affects that. So fixing the overall n, or fixing this, here I have, let's say this is a 2 by 2 table. I have one parameter here, I have 2 here, I have 2 here, and I have 4 here. And that's far too many. What I need for, say, an independence model is I only need 2 parameters, one here, with a fixed total. And so I want to see how I get rid of that. So let me draw one of these matrices. So let's say we have these 2 variables, a, b. What is their outcome? Suppose they only take 2 states, so they could both be 1. So A could be 1 and B could be 1. A could be 1 and B could be 2. A could be 2 and B could be 1. A could be 2 and B could be 2. So I have a matrix, and I want to I've labeled the columns of this matrix with possible outcomes. I can also think about these as representing cells in the contingency table, counts, or probabilities, depending on which table we're thinking about. We can also label the rows, and we can label the rows by these parameters. So the first row I could label with the parameter that corresponds to some kind of global total. A second row for A being 1, another for A being 2, another for B being 1, and another for B being 2. So this is just for the independence model. I'm not even dealing with the interaction yet. So here's my 5 parameters, which are too many. And I want to think about this matrix as computing the count. So if I plug into this a table of outcomes, like say, oh, I saw 3, 5, 1, 2 when I ran my experiment, the row that corresponds to lambda should count the grand total. So what is a grand total? It's the event something happened. So what, if I want to know what the grand total is, what should I put in this row?
1, 3, 5, 1, 2.
That's what we want the output to be. We want the output to be the grand total, which is the sum of these, right? 11. So how do I get 11 from that? So if I think about it as matrix multiplication, I have 3, 5, 1, 2. And I'd like the first, I'm going to multiply this by that. I'm going to get a matrix. I'm going to vector.
Oh, just 1, 1, 1.
1, 1, 1. A vector of counts, right. 1, 1, 1, 1. Okay, so multiply that, and I get here 11. Right, this is the number of times that we saw something happen. So for this parameter, lambda 1a, or lambda a1, what should I be counting?
1, 0, 0, 0. No, so 1, 0, 0.
So what, yeah, right. So that's right. So what am I counting here?
The number of times a was equal to 1.
Yeah. And this depends on the the way that the order that I wrote this in. Maybe it's not. No, that's right. Right. A is 1 here. A is 1 here. Yeah. Okay. So the number of times a is equal to 1 is 8. Well, how about for this one? 0, 0, 0. That's the number of times a is equal to 2, and in this example, it's 3. And for this guy, number of times that b is equal to 1. Sorry?
1, 0, 1, 0.
Yep. So that will be 4. And the last one, 0, 1, 0, 1. Okay. And that total is equal to 7. All right, so for a Poisson model, for a Poisson independence model, I should have 3 parameters. For a multinomial independence model, I should have 2 parameters, right? 'Cause I'm fixing the count. So how do I see the numbers 3 and 2 in this matrix? Number of parameters of Poisson model. Number of parameters, number of free parameters, number of degrees of freedom. We're calling this degrees of freedom. Multinomial model. Right. From drawing the picture of the multinomial model, you also know this is the dimension of something, right? It's the dimension of that independent surface. The reason it's not 3 is because everything on that surface assumes that the probability sum to 1. Right? So how do I get 3 and 2 from that matrix? I can read them off. They have nothing to do with this. Well, okay, so I told you this was over parameterized, right? If I use all 5 parameters here, I only need 3 parameters. It's over parameterized. That means if I know some parameters, I can compute others from it, right? If I know some of these, I can compute others. So, right. So there's redundancy among the parameters. Okay. This is a matrix. The rows are redundant. So how do we measure redundancy or independence of rows in a matrix? The rank. Right? So this number is the rank of this matrix. Let's call this matrix A.
So at that time, the rank of A is of 1.
The rank of this matrix is 3.
3.
Yeah, if you did a Gaussian elimination or if you asked yourself, right? So like this plus this is equal to that. And this plus this is equal to that. That's basically what's going on. In other words, I could erase this row, right? I could erase that row, and I could get it back by taking this minus that. I could erase that row and get it back by taking this minus that. That's the redundancy. That's the exact same redundancy as saying I can encode this variable as being 0 and this one as being 1, or I can encode this one as being 0 and this one as being 1. Right? The outcome of A equals 1, I could encode with a dummy variable x, which is 0 if it's 1 and 1 otherwise, or I could put the 0 here. Same way, same choice I have here. And that redundancy is the exact same redundancy as saying that this matrix has rank 3. And then if we're saying that the global count is part of the input, and we don't care about estimating the global count, or we want to normalize, or we want to ask about probabilities, this vector here, this row vector here of all ones, is the global count. Right? And so we really care about, if we have to subtract 1 again, because this parameter is kind of fixed for us by the grand total that we're given. And so this number here is the rank of A minus 1. And this matrix here is sometimes called matrix of sufficient statistics. Because in this particular model, all we care about is the global total, what happens with A, what happens with B. And so the sufficient statistics are just the counts, the global total, how many times A was 1, how many times A was not 1, how many times B was 1, how many times B was 2. Right? As I add interaction terms, I have to add more rows to this matrix that correspond. I have to add rows to correspond to interactions, to things like A and B are both 2, would be another row. Of course, I could add another row for A is 1 and B is 2, B is 1. But what would happen is that they would be redundant. So I would only need one more row to get the full independence model, or the full saturated model.
What's the corresponding word variety to this matrix?
This is another just independence model, another way of writing it.
But for the multinomial independence, which one does this, the image, which one produces the image, which is the corresponding varieties? The multinomial, the Poisson?
This is the affine basically dimension, this projective dimension. If that makes sense. Yeah. And we have too many. With this setup, we have too many parameters. We have redundant parameters. There's relations among them. So then, if we wanted to add, I could add another one for lambda ij. I'd add 4 parameters. There would only be 1 effective parameter added, because using all this information, I could do row reduction and get back to one of the others.
Yeah, I was wondering, so can we think about in a general case? So here we can think about the 2x2 case. So the rank of the A is 3. So if we think about 3 by 3, can we say kind of if 3 by 3 gonna be 9 minus 1, right, for the rank of A? We write it as a matrix form.
Well, this A depends on the model.
Yeah.
So you should think about this as this is an independence model, maybe. If I write a different model, it'll have a different matrix. But you can always compute that degrees of freedom of the model by computing the rank of this matrix, which is like a sufficient statistic matrix. And that fact extends to arbitrarily complex models, log linear models. Right, so in order to correct this, So it's overdetermined. The fact that it's not overdetermined, it's redundant. Redundancy. So we have redundancy. We don't like redundancy because it will break our identifiability and sort of in principle break our asymptotics. So we can get rid of it by removing some parameters. So I can go down to a simpler matrix, like 1, 1, 1, 1, lambda A1, which is 1, 1, 0, 0, lambda B1, which is 1, 0, 1, 0. So I could use this. That's equivalent to choosing the baseline that sets, I think, A equals 2 and B equals 2 as baselines. Or I could do the other one where I put in lambda A2 and, oh, let me write that. 1, 1, 1, 1, lambda A2, lambda B2, 0, 1, 0, 1. Right? This sets A equals 1 and B equals 1 as the baseline. Or I could do something possibly more exotic, take some other linear combination. And what is this model theorizing? I guess it's just erasing it right now, but in other words, what is this model predicting about these entries? Well, mu11, according to the log linear model, is what for this independence model that we've written over here? For this one. It's a combination of these lambdas, right? More or less what I just erased.
I was wondering, can we try to see the lambda plus the lambda A1 plus lambda B1?
Yeah, that's right. Lambda plus lambda 1a plus lambda 1b. Log mu12. I'll give you the first one. So what's this one? Yep. And 2, 1. What about 2a and 1b and the 2, 2. And we're still doing an independence model, otherwise we would have some more terms. Lambda 2a, lambda 2b. Right. And so these things are just you just read them off from the columns of this matrix. Right? This is the column. This is the first column. 1, 1, mu11 is lambda plus lambda 1a plus lambda 1b. Mu12 is log mu12 is lambda plus lambda 1a plus lambda 2b. Same for the third column. Same for the fourth column. Right? So these are just from the columns. Matrix. Let's see if we can get this right. So what we're saying is that log mu equals I think we want to say lambda, maybe lambda transpose A, right? If we have a vector of mu's and a vector of lambdas, we want to write this as a matrix equation. Just saying we're just multiplying on the left by the lambdas to get the vector, to get the entries of the of log mu. So there's one other way we could correct the constraints instead of removing columns. There's many other ways, I guess, but one other common way is we could add constraints like sum over I lambda I x equals 0, sum over j lambda j x a and b equals 0, right? So that's another way to sort of impose this constraint instead of reducing the number of effective parameters. That's a little bit more awkward to do in this kind of matrix format, but it's something that happens. So, and now I should tell you, okay, in SAS, so in the different software packages that you might be using, they made different choices about how to simplify this matrix in order to get something which doesn't have too many parameters. So in SAS, there's a proc gen mod, and that sets the last one to 0. Last level set to 0. So that gets rid of, in this case, that we cross out that row and cross out that row. So like log mu11 is equal to lambda plus lambda 1a plus lambda 2b, and log mu22 would be equal to what? In this 2 by 2 case. If we set the last level to 0 to simplify our equations.
Does it only set the last level of A to 0 or
Last level of each. Let's put x there. X, yeah, that's right. So it's just lambda. And that's just a convention. In R, it has this function GLM. The first level is set to 0. Of course, you can change these, but this is the defaults. So this one is equal to lambda, and log mu22 is lambda plus lambda 2a plus lambda 2b. Yeah, it's the sort of dummy encoding that's closer to what we've usually done, where the second state of the variable is encoded as a 1. So you need to be aware of that because obviously depending on which piece of software you use and which setting you use, you'll get a different answer. And you have to be aware of why that answer is coming out and how to change it back to the other one if you need it for a question. In SAS, there's also a proc cat mod. And R, there's a log lin. And these use that zero sum constraint. Log mu11 is lambda plus lambda 1a plus lambda 1b. And then log mu22 equals lambda plus lambda 2a plus lambda 2b, which is equal to lambda minus lambda 1a minus lambda 1b by this sum to 0 constraint. Okay, so these log linear models are joint models. There's no distinguished dependent variables other than the counts themselves. But of course, sometimes they translate directly into like a logistic regression type of model. And in any case, it's useful to think about what the conditionals would be or what the odds ratios would be in this. So for example, if I could take logit of p y equals 1 given x equals I, or log probability that y equals 1 given that x equals I divided by the probability that y equals 2 given x equals I. So that works out to be log mu I1 over log not I1, which is just I2, 1 minus the first, well, the corresponding thing. That's the difference of these logs. And then plugging in our parameters, our model, that's lambda plus lambda IA. Let me switch to x and y. Plus lambda IY minus lambda plus lambda IX plus lambda 2y, which is equal to, most of the stuff cancels out, and you get lambda 1y minus lambda 2y. Okay. So what's going on here? Well, we assumed independence in this model, and so the answer we get here doesn't depend on I, doesn't depend on x, because we assumed that these variables were independent. In other words, our assumption is that in each row, the odds of y equal to 1, which is what we calculated up here, in each row, independent of x, the odds of y equals 1 is e to this number, lambda 1y minus lambda 2y. So our result, or our sort of inference, depends on just this difference. And these sorts of differences, the odds ratios, the log odds, the stuff that we actually want to ask on the table, are unsurprisingly, hopefully, going to be independent of the choice we made. So they depend on where we are, and not sort of how we got there in terms of which thing we decided to set to 0, or the particular encoding that we chose. So different constraints, these three different choices of constraints, first, last, or sum to 0, will give us different parameterizations, and therefore different parameters with different interpretations. What you can get one to one from the other. But these sort of differences, or these log odds, will be unique and will be invariant. Okay, so now let me expand this to the saturated model. Yeah.
What is your freedom for this model? Whether because we added the three constraints, or whether say we just the degree of the freedom for the model gonna be the
Right here.
you mean through 3?
Well, 3 if it's a Poisson, and 2 if it's a multi. In other words, if I fix the grand total by my experiment, I don't estimate it, then it's 2 degrees of freedom. If I'm estimating that grand total, then it's 3 degrees of freedom.
So how do we actually solve for these lambdas?
Well, in some cases, like the saturated model example from last time, or in the independence model, you can do it by hand. In general, you need to optimize to solve for the lambdas.
But using what, like solving like a GL, isn't that what these are?
Yeah. Right. There's the easiest to understand. So there's this algorithm called iterative proportional fitting, which was one of the first algorithms for solving this kind of models due to Feinberg. Of course, it's now 30 or 40 years old, and so there's been many revisions since then. But this algorithm is the one that will feel natural to you, because what it does is it moves along the toric variety by iterating on these parameters, like by increasing or decreasing those parameters according to how close the match was. So that's one way you can do it, is you have this model surface, and you have this parameterization into the surface, and you can do an algorithm which iteratively moves along that surface to a better point. Conceptually, that's probably the clearest algorithm to look at. I probably won't get into the details of it, but something you can examine maybe in a project or whatever if you're interested. And then there's others, so sometimes it works better to say, oh, I'm going to temporarily allow myself to get off the surface and project back. And, there's lots of other strategies for optimizing. But there do exist strategies that kind of work in these natural coordinates to solve the optimization problem and correct at each stage. All right, so let me add a saturated model. So this would be, excuse me, let me revive our pictures for a second here. Just because now we have some more label sense that we can add to these things. So say I have two variables x and y. I can add, in the independence model, I have only parameters lambda I, x for each possible state of this, possibly throwing one out or otherwise adjusting for this constraint. I have one parameter for each state of y. That's the independence model before I have this. If I want to allow for interactions, I now get I times j parameters. They're redundant, but I get I times j parameters naively, which are, I could label like lambda ij xy. I'm writing that out. This would be like a log mu ij equals lambda, and then there's this lambda global parameter. Plus lambda I x plus lambda jy plus lambda ij xy. So these are the association terms expressing deviation from independence. And an easy way to see how that's going to be simplified is that suppose we choose some constraints. Like we decide to set the last row, equal to 0. If we set the last row equal to 0, then the coefficients of the indicator variables, I'm just leave that matrix up. The coefficients of our dummy variables, our indicator variables, are going to be, of course, lambda 1 x, lambda 2x, lambda I minus 1 x, and I don't need the last one because I set it to 0, lambda 2 y, lambda 1 y, lambda 2 y, lambda j minus 1 y. For the first I minus 1 categories of x and the first j minus 1 categories of y, and then lambda ij xy is the coefficient of the product of the indicator variables in the linear expression. And I only need it for the first I minus 1 and j minus 1 categories. And there are I minus 1 times j minus 1 such products involving only the first two, with the constraint that the last one is equal to 0. And so you recognize this number for the number of interaction terms in an independent. Starting with an independence model, I added an interaction term to the two-way table, and I got this number, which is the number of, I'm saying this is the number of coefficients for interaction terms. So if there's any interaction, some of these should be non-zero. this number is the degrees of freedom for the test of independence, right? It's the number of ways that it can fail. And now we have explicitly an exact match that gives us one parameter for each way that it can fail to be independent. One of these coefficients. So when all these coefficients are 0, or indistinguishable from 0, it's independence. And this is the number of degrees of freedom for the chi-squared test of independence, the g squared. Let's look at the odds ratios in this picture in a 2x2 table. Now log theta log mu11 mu22 mu12 mu21 log mu11 plus log mu22 plus log minus log mu12 minus log mu21. And then I plug in the model estimates of all this with a saturated model. So I get lambda plus lambda 1x plus lambda 1y plus lambda 11xy plus lambda 2x plus lambda 2y plus lambda 2 xy. That would be 2 plus, or minus rather, lambda plus lambda 1x plus lambda 2y plus lambda 12 xy minus lambda minus lambda 2x plus lambda 1y minus lambda 21 xy. So I'm not saying anything about what those parameters are. If I plug in the model, the saturated model, that's what I'll get. And of course, lots of stuff cancels there. That works out to lambda 11 xy plus lambda 22 xy minus lambda 12 xy minus lambda 21 xy. So when I change, it's that total. This is the odds ratio, which is kind of invariant under many different manipulations, right? I change my probe vector respective, I change my dummy encodings. That shouldn't change when I change or what we're calling constraints, which is sort of equivalent to dummy encodings. For example, if I set lambda ij equal to lambda big ij equals 0. So I use this sort of last, if it includes anything at the end, if it includes any of the last components that at 0, then all of this gets zeroed out here. And I'm just left with one parameter, lambda 11. Right? So though it looks like 4 parameters left in the odds ratio, it's really just one parameter after accounting for redundancy. And which encoding I choose, if I set the first thing to 0, so this is if I cut out this row and that row. If I cut out the other 2 rows, I would get first row, I would get lambda 22 as my parameter for the odds ratio. But I'll get the same odds ratio. So just a quick example, and I'm done. So suppose I have a 2x2 table, and the log odds is 2. and I set lambda xy ij equals lambda xy ij equals 0. So I set the second, the dummy variable is 1 if the first category is hit, and 0 if otherwise. Then I'll get 2 equals lambda xy 1, 1. It'll be the coefficient of the dummy variables for x equals 1 times dummy variable for y equals 1. And if I set a constraint like this, like those latter two procedures in SAS and R, then I'll get lambda 1, 1 xy equals lambda 2, 2 xy equals 1/2, and lambda 1, 2 xy equals lambda 2, 1 xy equals negative 1/2. So all four of these things will have non-zero numbers, as I'd expect, because I use this kind of constraint instead of zeroing anything out. But log theta equals this sum, lambda 1, 1 xy plus lambda 2, 2 xy minus lambda 1, 2 minus lambda 2, 1. And plugging those in, it'll be 2 again. Okay. So no matter what constraints I choose, no matter which rows I choose to keep in, as long as they're the right, they're a spanning set, I will still get the same odds ratios. But just, I have to change my interpretation a little bit to match the dummy variable choice that I made. Okay, so let's stop there.